Pair production is a phenomenon where a photon gives an electron and a positron. It's a direct demonstration of the Einstein formula E is equal to mc². But there is a catch here. Even if a photon has more than enough energy, the reaction cannot happen in empty space. It needs someone, a partner. Why does light need help to create matter, and who plays this partner role? Let us find out in this video. In physics, no matter what process we talk about, whether it is photoelectric effect, Compton scattering, pair production, or any other example, one golden rule applies. That is the conservation law. And this can never be violated. Energy, charge, and momentum must always be balanced, and if one of them fails, the reaction simply cannot happen. Now let us see the conservation laws in pair production process. Now let us apply the conservation of energy in pair production. The rest mass energy of electron is 0.51 mega electron volt, and for positron is also the same. So we get a sum of 1.02 mega electron volt. So the photon must have at least this minimum amount of energy, and the electromagnetic wave spectrum falls in high energy gamma ray spectrum. And if the photon energy is more than this, it will be reflected in the form of kinetic energy of the electron and the positron. Now let us see the conservation of charge. Photon has a charge of 0, electron has a charge of -e, and the positron, which is the antiparticle of electron, has a charge of +e. So the net charge of this electron-positron pair is 0, which is equal to the charge of the photon. Here we see that the charge is conserved. Now let us check the conservation of momentum. Photon is a massless particle, but we can assign a momentum using the relativistic relation. And let us assume that the two matters, that is electron and positron, they are flying off at an angle theta. So the horizontal component will be p cos theta. The vertical component will be cancelling out because the photon is traveling along the horizontal direction. So the vertical component of electron and the positron, it has to cancel out. Equating the two momentums, we have this relation. It is h nu is equal to 2pc cos of theta. In this relation, let us substitute the expression of p using the relativistic momentum expression. So we get this. Now here v by c will be less than 1 and cos theta will be less than or equal to 1. Using these two conditions, we have h nu less than 2 gamma mc². Now let us check the relativistic total energy of the photon. So we have this relation, and from this relation we can write h nu is equal to 2 gamma mc². Now if you compare these two relations, one is equal to and one is less than, this means that momentum is not conserved. So pair production cannot occur in empty space. For pair production to occur, we need an object or a partner nearby to conserve the momentum, because we have seen earlier that momentum is not conserved. So who is this partner? Most of the time, it's a nearby nucleus. Why nucleus? Because the nucleus is very heavy compared to the electron or positron, and it can absorb a tiny recoil momentum without gaining much kinetic energy. Now the next question is, why not just an electron instead of a nucleus to conserve the momentum? Technically, it could happen, but the problem with this is the electron is light. So when it recoils, it carries away a noticeable chunk of energy that leaves lesser energy available for creating the matter. Before I wind up this video, I would like to mention an alternative process for the creation of electron-positron pair, that is the photon-photon collision, where two high energy photons give rise to electron-positron pair. Here one of the photon provides the energy and the other provides the recoil momentum. But this process is very rare, and happens in particle accelerator or astrophysical environments. So in summary, pair production cannot occur in empty space. It requires a partner to conserve its momentum, and most of the time this partner is the nucleus. Thank you everyone for watching this video.